Welcome to IBM Think 2025.
If you're going along the route of classical computing, you do eventually get to machine learning, you do eventually get to AI. And if you want to start thinking about computing in a different way, you have to introduce quantum mechanics. There's no other option.
And why is this the case?
Quantum mechanics is the most accurate model of reality, but you can't visualize it, you can't picture it, and I can't describe it to you perfectly. Nobody can. We don't just want to wait for this technology to mature to use it. We're creating algorithms that can be used for the quantum computer at the same time as we're perfecting and improving the quantum computer itself.
It's the future.
We certainly think so, yeah.
Please welcome Director, Mathematics of Computation, IBM, Zaira Nazario.
Good afternoon, everyone. Welcome to the last keynote of Think. Really, thank you for being here. Some of you glass in hand, as it should be, right? My name is Zaira Nazario, and I lead our Mathematics of Computation group. And I'll say, doing research at IBM is really an incredible job. We have experts in high-precision computing, AI, in quantum computing, in hybrid cloud, that all come together across labs all over the world. And although the disciplines and the science are broad, we're all united by a common purpose, and that's being the organic growth engine of the company and invent what's next in computing. So computing. I want you to think about the role of computing in our lives. Because once we turned computers on, we've never turned them off. So think about it. It's pretty remarkable. And not only that, but we rely on them more and more. Our modern world was built on the back of bits, the underlying unit of information powering high-precision computing. And we kept building ever more powerful machines and forms of computing with different flavors. We've seen the rise of AI and LLMs that seem to be refashioning our world in real time. And the latest addition to the computing family, that came from a fundamental rethinking of the very nature of information. That's quantum computing, where we're harnessing quantum mechanics to launch a completely new form of computation. So each of these technologies offer vastly different and powerful capabilities. And at IBM, we're not just focused on putting each of them to work, we're actively investigating ways of bringing them together to create new capabilities that are already proving to be valuable. A prime example of that is how we brought the virtues of generative AI right into the heart of Z17. That's a taste of what's to come, because to uncover the value of these intersections, we formed the Mathematics of Computation group. And the team is working very hard to develop the mathematical frameworks and the advanced algorithms to foster those connections between our high-precision computing, AI, and quantum systems, and to realize their potential to solve those complex mathematical problems that move businesses. I'm really very proud to be a part of a rich history of theory at IBM, where we've used mathematical reasoning pretty extensively in the development of algorithms. And in fact, a few years ago, MIT analyzed the contributions of institutions to the most important families of algorithms. And guess what it found? Look, many people develop their own mythologies about how science and innovation work, about where the best work is done and by whom. And well, that study showed that IBM has contributed the most and with the most impactful algorithms for science and business. I think we can say that algorithms run our digital world, and IBM has a pretty long tradition in this space. And combining our work in this space with our contributions in things like material science, in nanotechnology, in semiconductors, we've laid down the foundational technologies that have launched entire industries. I mean, like just take as an example how we invented automated fab with the EDA. That launched an entire industry worth tens of billions of dollars. And that's just an example, because really we've been pushing the computing industry forward for as long as there's been one. But if you ask me, what I find most exciting about my job, well, there are many things, no doubt. But I think it's that me and my team get to work closely with the top minds leading research in all of these technologies. I find that very special. And today, in an Audacity of Computing scope, I have two of those colleagues that will share with you the extraordinary things that they're doing to invent what's next in AI and quantum computing. Starting with how we're going to cast off the fetters that are holding LLMs captive. And for that, please welcome our VP of AI Research, Shuran Raghavan.
Good evening, everyone. It's always wonderful to be here at Think to share our perspective on technology with our clients and partners. It's such a wonderful opportunity to talk about computing and where it's going, almost independent of specific products and offerings. And certainly in the world of AI, we've had a chance to really explore a technology that's moving at a tremendous pace. And we have continued in the research keynote to evolve, sharpen, or refine our thinking. So let's take a quick trip down memory lane and talk about what we talked about on AI in this keynote over the last 3 years, a 30-second trip down memory lane. So it was in 2022 that we first introduced and shared the science and structure of foundation models. We talked about how this technology is poised to fundamentally change how AI gets done and fundamentally change the technology landscape. It was in 2023, again at the research keynote here, that we really talked about the importance of taking a platform approach. We said to get AI for real, you need to think across the entire life cycle, from the building, the customization, the governance of models. And we then introduced watsonx as the platform for you to extract value from AI in your enterprise. And then it was at 2024, again in the Think keynote, that we then talked about the importance of data. We said the most precious resource in every enterprise has is data. And to truly get value from AI, it was important to be able to get enterprise data into the LLM. That's when we announced our open source family of fit-for-purpose Granite models as a trusted base for you to build and do that. And then continuing this year, you've seen the announcements around watsonx.data that continue the theme of the importance of enterprise data for successful use of AI. So LLMs, platform, data. So what's our big picture for 2025? You probably expect me to say agents, but there is a reason there is a question mark there. Certainly agents, they are the preeminent emerging architecture to help us build an entirely new class of LLM-powered applications. But what I want to share with you today is that there's something much more fundamental and profound that is underway. And it's something that we are beginning to call generative computing. And it's a recognition that an LLM is a fundamental new computing element that has come into our ecosystem. Yes, it's an interesting AI artifact. Yes, it's a representation of data. But it's actually a new computing element. And where there's a new computing element, you require new runtimes and new abstractions to work with them. So what I'm here to motivate you in the next 10 minutes to tell you that the way you get to build secure, efficient, and effective agents is actually to pull on this idea of generative computing. Now, you might ask, I'm building agents today. I'm starting to work with LLMs already. So why do I need generative computing? So let me motivate by stepping back a little bit and look at what we have tried to do as an industry in AI. In 3 short years, as models have become powerful, our ambition has become powerful. We started building simple chatbots, assistants. We quickly now moved to agents. Our applications have gone in complexity. The tasks we want to do have gotten in complexity. We were happy doing simple Q&A and summarization. We went from that to RAG, and now we want to call tools and orchestrate entire enterprise workflows. We were initially only working with simple documents. Now we are working with multimodal documents, speech, audio, video, touching SQL data, tabular data. So whether it is what we want to do, whether it is the task we want to accomplish, whether it is the data that we want to manipulate, we have exploded in complexity and ambition of what we want to do with AI. And it's therefore no surprise that we have seen an explosion of frameworks and protocols. I mean, this is just a sampling. I could fill an entire chart with icons about frameworks appearing to help you do RAG better, evaluation tools, connecting tools to agents, talking between agents. There's frameworks for all of these things, and rightfully so, because you are trying to do more complicated things with AI. But yet you step back and ask yourself, has the fundamental mechanism for interacting with models changed? No. We continue to do prompt engineering. And our prompts have gotten larger and larger and even larger, and very soon we're going to have books and books of prompts. That is untenable. So we have all of these frameworks, but we have to rethink how we are actually going to go work with models. And today I'm trying to unpack for you why generative computing is about building those abstractions around models. So let's look at the problem. OK, what's wrong with writing books and books of prompts? So I'm going to use this little running example. This is actually an agent that is used to produce research reports. You can actually see an instance of this agent in the Think forum. The first observation is, this is complex. And by the way, this is a simplified prompt. I'm not expecting you to read that English, but this is a simple prompt for an agent. So you'll actually recognize this is not maintainable. This is really not maintainable. Let's dig in now to a portion of this prompt. So I'm going to go look at a portion of the prompt where the model, you are instructing the model on security aspects, what you want the model to do and don't. And I will encourage you to read it. I call this security by prayer. You're imploring the model not to do something and not to do it. That is certainly not a robust way to do enterprise applications. And it's open to all sorts of exfiltration and attacks. Now let's look at a different section of the prompt. Same prompt, but I'm now going to go scroll and look at a portion of the prompt where if you read that section in red, you see that it's very carefully crafted. The agent is instructing the model exactly how the output report should be structured, what should be in it, what should be not in it. But what it's observing here is it's very carefully crafted. Some things are in bold, some things are not in bold. Sometimes you have to tell the model twice that you don't want a conclusion in your report. What does this tell you? It tells you that this is extremely brittle and engineered for a specific model, which means there is very, very high likelihood, and actually it happens in practice, then when you try to take the same agent and apply it to a different model, you're going to have to do that prompt engineering all over again to get acceptable accuracy. So the point we are making is we have expanded the ecosystem around models, but when it comes to interacting with models, we continue to remain using prompt. And the last but not the least is a big prompt like this typically requires a large model to make sense of all the English. So you are now taking a large prompt, running it against a large model, therefore requiring a lot more resources. So what I'm here to tell you is that generative computing is a way to move away from prompting to real programming. It's to recognize that an LLM is a computing element and to really build enterprise-grade applications that are efficient, secure, portable, and maintainable. There is a different way to think about how to interact with LLMs. So I'm going to unpack this a little bit and start to tell you what is the difference between pure prompting and generative computing. So the first thing is, when you do prompting today, you have an application. It talks to an API, through an API to a model. But you are transacting in the world of tokens. You are instructing the model through the world of tokens. It doesn't matter what the API is, but that's your currency for controlling the model. Now, with generative computing, here is what we're going to do. We are actually going to replace the API with an actual runtime. The runtime exposes a set of principled abstractions. This is the abstractions for generative computing. And when you expose a set of abstractions, you now have a much more structured way. You replace that prompt with something that actually looks like a real program, because an agent is a program that you're developing. Now, I'm not going to spend time on every one of these things, but I just want to give you a flavor for what those abstractions look like. So let's look at that same example that we wrote in pages and pages of English and ask ourselves how you would do it as a generative computing program. So I'm going to quickly walk through. Here are 3 or 4 abstractions we are looking to develop. One is the notion of a guardrail, a structured way to specify the security properties of what you want the model to do or not do. Then there is a notion of requirements, where in a very structured way, you tell the model what it is that you want the model to do. And remember, you're not doing it simply by writing English that hopefully is correctly interpreted. You have explicit calls that the runtime understands and implements. And today here you see examples of requirements on syntax, on language, etc. And the runtime can enforce and check these constraints because it's a piece of software sitting in front of the model. You can have instructions that you want the model to follow. And then you put this all together with an abstraction that's called a generation strategy. You instruct the runtime. Are you going to talk to the model once? Are you going to talk to the model multiple times? Are you going to try different answers and sample? There's a lot to unpack. Now, I'm not going into the details, but let me give you some examples of how this change is dramatic. So the first benefit of doing this is that you're going to have way better efficiency. It's a concrete example. That same prompt that we have seen, when we were doing it with prompt engineering, required a way bigger model to get acceptable accuracy than by using with generative computing. Very, very specifically, that example, to get reasonable accuracy that was usable, something that required a 70 billion parameter model, with generative computing, we're able to do with a preview version of a model that uses no more than 1 billion parameters at inference time. Way more efficient. Second, you heard me talk about security by prayer. That's not quite how you want to do enterprise grade. In the world of generative computing, security was a first-class citizen. So the runtime will expose abstractions of what you want to do. You want to check for hallucination. You want to check for prompt injection. You want to check for other kinds of attacks. Each of them will make changes to the model. You will register appropriate LoRa adapters that will then implement this in the best approach. As opposed to hoping that a piece of English will get correctly interpreted, you have well-trained adapters that are going to implement security checks, a much more controlled way to do security. And finally, because now you have a runtime, you get portability. Yes, you have to adapt the runtime to different models, but you do not have to change your application code every time because you're not programming to meet the whims and fancies of individual models. You're programming to a structured abstraction. So the takeaway message is that generative computing recognizes that an LLM is a computing element that you're going to program, which is different from the fact that you can bring natural language applications to the user, but when it comes to a computing element, new abstractions are going to emerge. That's going to make building agents and applications efficient, secure, portable, and maintainable. And at IBM Research, we are doubling down on this idea of generative computing and evolving both our model strategy and the runtime strategy. We're developing a Granite runtime that's going to embody these abstractions. And we're also releasing the next generation of our Granite models that will come out later this summer. On our models, we're very excited that our next generation of our Granite 4 models will come in a number of sizes, from something that run on a little GPU on a device to models that you can use to do agents and powerful applications. These models exploit a new architecture innovation that combines state space models, which are very efficient, with transformer approaches, all packed in a mixture of experts approach. We are estimating with early benchmarks that this is going to give us 2 to 5x advantage over comparable models. So we're very, very excited about this direction that we are pursuing. It isn't every day that a new computing element shows up in our industry. So when something that like that happens, it's very, very exciting to be able to build new technology and new ways of building applications. So hopefully you will all join us in this journey to make generative computing real for the enterprise. With that, thank you for your time. And I'll turn this back to Zaira.
Thank you, Shriram. All right. So yesterday, Arvind told us that AI is moving from experimentation to production. And Rob told us about the billion and more applications by 2028. Well, I hope it was clear from Shriram that to make that transition and to get more sophisticated in what we do with LLMs, we really need to move from prompting to programming. And please, whatever you do, please don't do security by prayer. It's really not a good idea to do that. Now, Shurram and his team bringing you maintainable, portable, efficient, secure computing with LLMs. That's an example of how we're simplifying things to their essentials and realizing their greater implications for enterprises. Right? We're really making cutting-edge technology being more performant, more consistent. We're making them more cost-effective and flexible. And there's another example of how we're doing this, how we're pushing the capabilities of cutting-edge technologies and defining new computing frameworks. At IBM, we've been setting the pace in quantum computing for about a decade. And progress is accelerating. Right? We're advancing our processors. We're innovating in how we handle and correct errors. We're bringing these systems to other forms of computation. And we're developing algorithms to unlock the value of heterogeneous computing approaches using quantum systems. And now, quantum computing is quickly approaching a very important inflection point. So to tell us about it, please welcome our VP of Quantum Computing at IBM Research, Jay Gambetta. Come on here, Jay.
Thanks, Zara. So I get to talk to you about quantum. At IBM, we're actually been a leader in quantum research for over 40 years. But in the last 10 years, some pretty exciting things have happened. We were the first to put a quantum computer on the cloud in 2016. 1 year later, we were the first to create an open source software development kit for programming quantum computers, which we called Qiskit. And in that same year, we created the IBM Quantum Network. This is a community of academics, enterprises, national labs, all working towards the goal of discovering new algorithms or use cases that use quantum computing. Since then, since that first quantum computer, we've actually deployed over 80 quantum computers. We have over 600 users using quantum computing, and we've grown the quantum network to over 275 members. And using all our learning and material, we've touched over 10 million students. But things are only actually going faster. And so I want to look back at the last 3 years. So in 2022, we had a huge result. We actually broke the 100-qubit barrier. We did this with a device, the IBM Quantum Eagle processor. I want to give you some context. Imagine you had to represent qubits by bits, and I gave you 10 qubits. It's only a few kilobytes to represent this. So as we go forward, and imagine I had 30 qubits, and you had to represent it, that's equivalent to a laptop. At 49 qubits to represent it, it's actually equivalent to some of the biggest supercomputers we actually build. At 100 qubits, we would need to build supercomputers about 10 trillion times bigger than the ones we build today to be able to represent 100 qubits. And with all the innovation we've done, we're actually at 156 qubits now with our Heron processor. And so you can see the goal of even trying to realize even a 10 trillion times bigger supercomputer today is just impractical. So what have we done that allows us to get there? Why can we innovate so fast? The first is we're actually very good at IBM at semiconductors. I would say we are the only team approaching quantum computing as an engineering problem, not a research problem. To give some context, we actually make a new device every 17 days. Every 17 days, we come up with a new idea, we test it, and this allows us to keep that cycle of learning, keep that innovation, and push us to the next step. And that's what we did in 2023. We wanted to get to a point, we called it utility, and what that is that's when a quantum computer is actually able to execute accurately quantum computations that are beyond what we can do with a brute force classical computer. The key word here is accurate. If I had a computer and I couldn't trust the output, or it just gave noise, it's not actually useful. At IBM, we're not interested in running random circuits. We want to make sure we can get accurate results. And that was exactly what was recognized by the team working with our colleagues at Berkeley, we were able, for the first time, to run accurate results on a quantum computer at a scale beyond what you can simulate with classical computing. I'll give you some context. I know this plot has a lot of information, but if you go back, we're actually in the 100th year of quantum mechanics, and the art of making progress for those 100 years is actually coming up with ways of approximating. And so what's shown on this plot is results run on the IBM Quantum Eagle processor and various approximate solutions. I want you to take 2 key points from this. The first is all these approximate methods are actually different. None of them agree. And the second is the ground truth. The reality is the one run on the quantum computer. So this is huge. We're at a point where now running on a quantum computer is better than using a classical computer to simulate a quantum computer. So I've told you we've got to a point where it's impossible to represent on a quantum computer. We've got to a point where it's better to run a quantum computer than simulate a quantum computer. But for all of you out there, you want to know, when is it better to run a problem on a quantum computer than compare it to running it on a classical computer? That's when quantum is finally giving you what we in the field call a quantum advantage, where it's actually cheaper or faster or more cost-effective to use a quantum computer over a classical computer. So originally we thought about this, and it's not quantum versus classical. It's actually quantum plus classical versus classical, and if I can get a cheaper, better result, then that's a win. And so in 2024, we came up with this idea we call quantum-centric supercomputing. And that's just exactly what it is. It's a hybrid computing architecture that leverages both classical and quantum computing. So now we can start to consider some real problems. This is work we've done with our partners in Riken, and it's like simulate the ground state of a chemistry problem. And so you want to find the lowest energy of this problem. And so there are methods that exist classically that are either computationally easy to run, and they're ones that are really difficult to run, and they give you a pretty good result. And what we were able to do is come up with an algorithm where we run part of the problem on one of our quantum processors, and the rest of the problem is actually ran on Fugaku, one of the world's biggest supercomputers. And what is actually amazing is at this 45-qubit example of this iron-sulfur cluster, we are getting results consistent with the best classical methods. So now I'm comparing a quantum computer running it as a quantum computer to a classical computer running it as a classical computer, and we're getting results that are about the same. So now we want to go beyond that. We want to go bigger. And so we had to reinvent how we do this architecture. So in that first example, the team actually ran it on quantum computer and then emailed it to the team in Fugaku in Japan, and then loaded it up and run it on a classical computer. Obviously, that's not practical. So we have to go to this new regime where we have results that we have 2 accelerators. We either have Fugaku, a supercomputer, as well as a quantum computer. And now we want to come up with a way of orchestrating, being able to run on both of these. And unlike just having one accelerator, both of these are very expensive. So in this example, as we go through, you see that the users submit their program, and we've got to create an object we call a workflow manager, that if I left any idle time on a supercomputer, I'm wasting resources. Any idle time on a quantum computer, I'm wasting resources. So this is a real difficult orchestration problem. If we zoom in on the quantum circuit, what we find is here the quantum circuit runs, it goes to one of our Heron processors, the circuit comes in, it turns it into random ones or zeros, and now we send it over to the supercomputer, where we take the results of the quantum computer plus an extra classical script, run a bigger problem that gives us a new set of parameters to repeat and run this multiple times. And then we want to iterate backwards and forwards, running between the classical and quantum computer, having them all idolize. And so what I'm excited by is, this is only a week old, is we were able to go to a 77-qubit system and now look at a bigger molecule and actually start to see that we're also getting comparable results. We're not getting exactly beyond, and at this size, we even believe as a community that the lowest energy here may not actually be the real energy. So as we go forward, we should be able to get to a point where we're actually getting to what we call quantum advantage. For that reason, we're making bold statements because we're making progress in our hardware, as well as the algorithms that are getting done, that we believe quantum advantage will actually happen by 2026. Thank you. And it's not just us. It's a community of researchers. Every month, every week, new papers get put out on different examples. I gave you the chemistry example, but we're seeing examples in optimization, materials, and so on. And so for this reason, I do believe we're going to see quantum advantage in chemistry first. Second, followed closely, is examples in optimization. And then thirdly, there's a lot of exciting work in mathematical problems where the team are exploring AI, quantum machine learning problems that could even have an impact in AI in the future. So if you're excited by advantage, what's even more exciting, and what I want to leave you with before I pass it back to Zara, is, and this is what Arvin was saying, in a couple of weeks we're going to go into, in his keynote, a lot more details. We now believe that we have a roadmap to create a fault-tolerant quantum computer by 2029. That means we're going to scale this technology, go beyond what we can do today, and bring this forward. On that, thank you. Zara? Zara.
Thank you, Jay. All right, that was an impressive amount of industry first and progress in the last 3 years. And I'll say, look, building a quantum computer like System 2 and pairing it with a powerhouse like Fugaku, wow, it's truly a marvel of human ingenuity. All in service of modeling fundamental aspects of nature, of getting to solve what has been so far unsolvable, and of achieving what has been elusive to computers so far. And I mean, if that's not fascinating and exciting, I really don't know what is, right? So from generative computing to quantum-centric supercomputing, I think you can see the importance of the work that we do at Research for IBM, right? From anticipating the rise and the importance of LLMs for enterprises to providing the programming environment to extract the most out of them in advanced applications, and from surpassing 100 qubits to building the path to quantum advantage. But as I said at the beginning, we're aggressively investigating how these different ways to compute can come together. And I want to make clear, these are not dreams anymore. These convergences of technologies are happening already. Right? We're already putting AI right in the heart of transaction processing systems. We're already connecting HPC and quantum systems to enable quantum-centric supercomputing. And these connections will continue. Now, let me leave you with this thought. As you know, we're made of atoms, right? But we have meaning and capabilities that go beyond the atoms from which we're made, and that can only be unleashed when those atoms come together to form the complex system that's a human being. And a classical supercomputer has meaning and has more powerful and diverse capabilities than the transistors of which it's made. So in nature and in technology, we see this over and over again, that putting together useful building blocks into complex systems unleashes usefulness and capabilities far beyond those of the parts. This is why we are committed to bringing together HPC, AI, and quantum computing, to make a whole that will unleash new and powerful workflows and capabilities that far transcend the individual system from which it's made. That's what we believe is next in computing, and we'll be the ones that bring it to you. And so now, enjoy Fenway Park. That's going to be a lot of fun. Enjoy the cruise and the rest of Think. Thank you very much.